So we're going to take a look at an example in Module 5 here. The example we're going to go through is 5.2.1. So in this example problem here, they're asking us to consider a two-mass system, similar to like what we discussed in Chapter 4. And we can see it again here in this figure down here below, 5.2.1. Suppose the parameter values are given to us as m1 equals 5, m2 equals 3, c1 equals 4, c2 equals 8, k1 is equal to 1, and k2 is equal to 4. So we can go back down to our diagram and say, okay, there's our k1, our k2, c1, c2 right there. So we have all these values there, and there's our m1 for mass 1 on the top here, and m2 for the mass at the bottom. We can see there's an external load there, and our displacements are given by our x1 and our x2 right here. So they also tell us that our equations of motion are given right here. So we have two different equations. We refer to this as equation 1 and equation 2 as we go through our solution. Equation 1 is given to us as 5x double dot of 1, 12 times x1 dot, 5 times x1 minus 8 times x2 dot minus 4x2 is equal to 0. So that's our first equation of motion. Second equation of motion is given to us as 3x2 double dot plus 8x2 dot plus 4x2 minus 8x1 dot minus 4x1 is equal to f of t. So what they're asking us to do in this problem here is to put these equations into a state variable form. So now that we've had the opportunity to read through the problem statement, understand what they've given us, take a look through that diagram, the next step that we want to do is to create our setup page. So that's what we've done here on our setup page. This is exactly what we've done for all the homework and what I'm expecting for the exams. Label, okay, ME111. Example problem I'm working on here is 5.2.1. This is a state variable model of a two-mass system. Here are my givens. So they give us these two equations of motion, the one that we just discussed there, equation 1, and the second one, equation 2 there. And then I write down everything that was in this problem statement written out. I come over here in a nice clear manner. M1 is equal to 5, M2 is equal to 3, C1 is 4, C2 is 8, K1 is 1, and K2 is 4. And I can relate those back to our given diagram. So the next thing that we want to do is figure out what are they asking us to solve for. Well, they want us to find is to put equations in state variable form. So these two equations, my equation 1 and equation 2, we want to get into state variable form. So what I want to do is reference us back to our lecture slides here. We talk about this state variable model here. So models that consist of coupled first order differential equations are said to be in state variable form. So in order to get this in state variable form, we need a first order differential equations. So we need to take these. We can see that we had second order there with some of our x double dots. So we need to figure out a way to get this in the first order differential equations. So this form is also known as our Cauchy form here. This has the advantage over reduced form, which consists of a single higher order equation, because it allows the linear model to be expressed in a standard and compact way that is useful for analysis for software applications. So this representation makes use of vector and matrix notation. In this section, we'll show how to obtain a model in state variable form and how to express the state variable models in a vector matrix notation. So you can reference back, I'm talking about this here, to our lecture slides to get into more detail. But I just wanted to briefly cover, before we jumped into the solution here, what the state variable model is and how we're looking for this first order differential equations. So now we'll jump into our solution page. And now we can reference back to our problem statement and to our setup page for all the values that we need, what they've given us, and what we're looking for. So the first thing we want to do is we're going to use system potential and kinetic energies. So our displacements x1 and x2 describe the system's potential energy. The velocities x1 dot and x2 dot describe the system's kinetic energies. So if we take a look down here at our potential and kinetic energy equations, our potential energy equation here is 1/2 k x1 squared plus 1/2 k x2 times x1 minus x2 quantity squared. So that's what we say our potential energies up here are just x1 and x2, because you can see there's our x1 and there's our x2 values that we can plug right into our potential energy equation. But now as we're dealing with our kinetic energy equation, remember, kinetic energy is 1/2 mv squared, where v is velocity. Well, velocity is the first time derivative of our position function, or our x dots. So we look at our kinetic energy equation here, and we have 1/2 m1 x1 dot squared plus 1/2 m2 x2 dot squared. So with those equations, we now have a relationship for our potential and kinetic energies. So this indicates that we need a 4-state variables. So what that means is we also can take a look back at this and note that the model consists of 2 coupled second-order equations, and thus effectively a 4th-order model from what we have from the given problem equations in the problem statement. So knowing all this, we can now choose our 4-state variables to be our x1, x2, x3, and x4, where x3 is equal to our x1 dot, and x4 is equal to our x2 dot. So therefore, 2-state equations that we have right now, 2 of these are x1 dot is equal to x3, and our x2 dot is equal to our x4. Now for the remaining 2 equations, we can find these by solving equations 1 and 2 from the beginning problem statement for our x double dot 1 and our x double dot 2, noting that our x double dot 1 is equal to x3 dot, and our x2 double dot is equal to x4 dot. So now we want to go back for the next part of our solution and look at equations 1 and equations 2, rearrange and solve them for our x1 double dot and our x2 double dot. So that's what we do here. I rewrite out equation 1 and equation 2 right from our problem statement. So you can see there's equation 1, there's equation 2. You can see equation 1 is 5 x1 double dot plus 12 x1 dot plus 5 x1 minus 8 x2 dot minus 4 x2 is equal to 0. So I can rearrange this and solve for my x1. Now, the second equation was 3x2 double dot plus 8x2 dot plus my 4x2 minus 8x1 dot minus 4x1 is equal to f of t. That I can rearrange and solve for my x2 double dot and then plug in to get it down to first order rather than second order. So let's do this one step at a time. Let's just look at equation 1. We're going to solve equation 1 for this x1 double dot, which we remember now is going to be our x3 dot in order to get it out of our second order there. So what we want to first do is take a look at equation 1, realize there's a 5 up here in front, so we can divide both sides by 5 here, and rearrange and get our x1 on its own, x1 double dot on its own over here on the left-hand side of our equation. So we do that, and we end up with our right-hand side being 1/5 times, in brackets here, negative 12 x1 dot minus 5x1 plus 8 x2 dot plus 4x2, where we can now have these substitutions here. X3 is equal to our x1 dot, x4 is equal to our x2 dot, x double dot 1 becomes our x3 dot, and x double dot 2 becomes our x4 dot there. So we can make those substitutions now, plug in, we can say, okay, here's our x double dot here, we go down here, our x double dot is replaced by x3 dot, so that's where we get this from here, is equal to our 1/5 minus 12. Now we have here a x1 dot, where we can see our x1 dot here is our x3, so we can plug in an x3 there, minus our 5x1, plus now we have 8x2 dot, where our x2 from here is now an x4, so we can plug that in there, plus our 4x2. So this brings us to this whole equation here, which we can now see is the first order. So now we're going to do the same thing that we did for equation 1, but now we're going to do it for our equation 2. So for equation 2, we're going to divide by 3 and then solve for our x2 double dot. So we do that there, we divide both sides by 3, we end up with our x2 double dot over here, and we have the 1/3 times the negative 8 x2 dot minus 4x2 plus 8 x1 dot plus 4x1 plus f of t. So where we can do the substitutions, x1 dot is equal to x3, x2 dot is equal to x4, x1 double dot is equal to x3 dot, x2 double dot is equal to x4 dot. So we do that there, we can see, okay, our x2 double dot, we go here, our x2 double dot is an x4 dot, so we can plug that in there. This is equal to 1/3 times our negative 8. This is a x x2 dot, our x2 dot we can see is an x4, so we can plug in an x4 right there, minus 4x2 minus our 8x1 dot, where our x1 is equal to an x3, so we can plug our x3 in there, plus 4x1 plus ft. So now we have this whole equation here. So a thing to note, first, we note that the left-hand side of the state equations must only contain a first-order derivative. And that goes back to that slide we showed when we were talking about those equations. And second thing to note is that the right-hand side of the equations must not contain any derivatives of the state variables. So those are two things to note, and double check once you get down here to make sure you've completed this. So with that there, the next thing that we want to do is list the 4 state equations in ascending order from left to right. This is a great way to organize them if we need to do any more manipulations to them, and we can double check everything. So we have x1 dot is equal to x3, x2 dot is equal to x4, x3 dot is equal to 1/5. I rearrange these in ascending order from left to right. Negative 5x1 plus 4x2 minus 12x3 plus 8x4. And my x4 dot is equal to 1/3 4x1 minus 4x2 plus 8x3 minus 8x4 plus f of t.